Maybe it's MTN, which is stronger.
Oh, it depends on where you are. Yeah, it's sharing now.
Yeah.
Oh.
Clementine is not attending classes. No? Is paying her money and then she does not attend.
I only paid for this one this month.
But we only paid for this one. And then for classical,
I haven't yet paid. I haven't paid.
you want to attend. Classical must attend. That one will knock you down. That one. You need explanations. Only solutions, they won't help. Is the screen sharing now?
The screen is sharing.
Yeah, for classical, you need explanations. For this one, of course, solutions you can maneuver, but for classical, you also need with the explanations. This one, if you get the answers, some of them, they are just substituting formulas. You can see the way out. All right. All right. Which one do you want us to start with? Let's start with number 3, the easy one, this one. Show that without computation, A dot BC is equals to 0. Hint AB, A cross B dot C represents a parallel piped volume. So this one's 15 marks for mathematical. Show that A dot B cross C here is equals to A cross B dot C for number 3. 5 marks. Must be in a position to do that one. This one is just pure mathematics. There's nothing like physics. This one. So it's a matter of dealing with the components. We'll solve this one as well. So let's start with number 1. Where we are going to end, it's fine. We'll just continue tomorrow, no problem. Present the Gauss law in integral and differential form, which is number 1, 2 marks. So in integral and differential law, so this is the Gauss law. So you get 1 mark for putting it in integral form, and 1 mark for putting it in what? Differential form. And remember, on the question paper, these formulas, were they given? Let's check for 2023. I don't think they will give you this. Can you see it was not given?
Yeah,
I see it was not given. So you must know how to put it in integral law and how to put it in differential form, the Gauss law. Is it fine here? Then the second one, which is, I will forward you the interpretation of the symbols so that you familiarize yourself after this class. I'll forward the PDF for the interpretation of those symbols. Find the electrostatic field established by 2 long concentric cylinders having radii A and B, with A less than B, which means A is the inner radius, B is the outerward radius. So if it was with the B less than A, which means The one that is greater is the outer radius. The one that is greater here, it will be the outer radius. The reason why it's radii, we say it is the plural. When there are two or more radiuses, you don't say radiuses, you just call them radii. Having respective surface charge densities. So that symbol, it represents surface charge density. Whenever you see that sigma symbol there, it indicates the charge densities of A and B, charge densities of A and B in the regions. So first one, the regions, one inner, the inside of the inner cylinder. Then you want the charge densities between the cylinders. And then the three, the charge density outside the two cylinders, or 1B. So the two concentric cylindrical shells, radii A less than B, surface charge densities A and B by symmetry. The electric field E is ER multiplied by the vector of R. So in terms of writing, it will be like this. You don't put a comma there. It's E. In terms, it's bold, which means it's a vector. E is equals to E of R. Then in brackets, that R is a subscript down here. E of R in writing, then you put in brackets R, function of R. Then that R is a unit vector. It must have a head there. A unit vector, it must have that head there on top. R, unit vector. So the charge per unit length on a shell of radius R, the charge per unit length on a shell of radius R, where lambda is equals to 2 pi R, 2 pi R multiplied by the charge density. This one, was it given on the formula sheet? So from now, you must pick formulas that you are given so that when you are calculating, you know that these ones, when I'm going to write, I'm not given this formula. So we are checking for that lambda, 2 pi R multiplied by the charge density R. It was not given. Can you see? It's not here. So are you seeing that you are bringing the formula yourself? Class, are you seeing that?
Yes.
Yes. So those formulas that we'll be discussing here, you must jot them down to know that this formula won't be given. The Gauss law formula also, you brought it, was not given. So the three regions, we are supposed to calculate the charge densities for the three regions: inside, in between, and outside the cylindrical. So for R less than A, which means it's the one inside, for R less than A to be inside, which means it's the enclosed charge is equals to 0, which implies that E is equals to 0. For R, which means for the radius, we are talking of the inside of the circle, the enclosed charge. E is equals to 0. And in between, where R is greater than A now, but less than B, that is the enclosed. The charge there, it's lambda for the enclosed one. Lambda is equals to 2 pi A, where the radius is A, then you use the surface charge density A. So in our case, the ER is equals to lambda over 2 pi epsilon naught multiplied by the radius for this region, which is in between. But what is your lambda? What was our lambda? What was our lambda for this region? So you replace where there is lambda, you are replacing this lambda.
2 pi.
Yes, with the 2 pi A is the radius, A, and that is sigma A, which is the charge density. A for that radius. So you find out the pi and the pi, they what? They cancel out. We are no longer using this one now when we replace lambda. So which means I'll be left with the A, that sigma A, which is the charge density, surface charge density of A over epsilon naught times R. So that is the electric field. So the electric field as a vector, remember we said our E as a vector. If you want this E as a vector, you introduce that component, R, that R as a vector, as a unit vector. That R is representing the unit vector R, which is the magnitude, the direction multiplied by, divided by the magnitude. So in our case, you find the ER, which is a what? This is a scalar quantity. Why is it a scalar? Because this will give you a number. If you substitute all the values, they are going to give you a number. But this is a vector. Why is it a vector? Because this E, when you're writing, you put an arrow there in the head. You won't put in bold. We just added the arrow there. That's why now it's now an E as a vector, the electric field as a vector. So now we come and say ER is equals to, how do we find that R as a vector? So everything is there. We are having ER, E naught R, we are having E naught R. We still have sigma A. Sigma A, we are having it already. So what is that R which we have replaced there? What is the R that we have replaced for that point? So it's A, which means A multiplied by the charge density of A, which is inside. We are talking of inside that cylindrical. Remember the inner radius, and we have the outer radius. It's a cylinder, which is like a hollow. Then this side, we are also having the same thing, the inner radius and the outer radius. So the inner radius. So for now, we are only calculating the one which is in between, inside here, the one in between, inside, in between. We've already calculated the one inside. We said E is what? Is equals to naught, this one. For the one inside, E is equals to naught. For the one inside, which is less than, E is less than, E is equals to naught. Then now when we are calculating for the one, for the region A to B, the one in the thickness, which is in between, the enclosed one, lambda is equals to 2 pi A multiplied by the surface charge density A, sigma A. Then the formula for ER, this formula is not given. It's yours. You must bring it there in the exam. Lambda over 2 pi epsilon naught multiplied by R. You replace the value of lambda A, sigma A over E naught epsilon R. If you want to write it as a vector here, you just introduce the R component. Then when you are here, where ER is equals to, so we are now taking the radius times the surface charge density. Plus, why are we adding? Because it's in between. Because we have ER of the using the A radius. Then we have ER using the B radius, which means we are having two of these ones. That's why you are adding them, because it's in between. So this is as a scalar, which means it's as a scalar. As a vector, you are simply introducing what? The R component. So which means also if you want the electric field with the B component, the charge, which means here it will be B multiplied by the charge, surface charge density of B over the same. That's why we added here, because it's the one which is in between in the thickness. You can check the question which we are having for number 1, this one. Having respective to surface charge densities. So here we are finding the electrostatic field between the cylinders, which is Roman figure 2. So now you want the electrostatic field between outside the cylinder, which means it's 1, 3. Now that is the one that we are calculating for 1, 3. So using the differential form, grad dot E is equals to that rho over epsilon naught. Grad dot E is equals to rho over epsilon naught. But in our case here, for number 2, our answer here, for number 2, our answer is this. You end here for number 2. For number 2, it was Roman figure. It is B2. Then for B3, that is the one that we are supposed to be solving now. For B3, the one for the region outside. For B3, that is the one that you need to solve for the region which is outside. For B3. All right. Then for the region, for A, 1A, we said E naught. Then for the region which is enclosed B2, we gave our answer. The electric field, we added the two sums. So the signs of sigma A and sigma B. Then the one which we are doing now is C, isn't it? For C, what is it saying? The electric field in a particular region is given by E. Calculate the charge density in that region. This one is just formula, this one. If you know your E, then you just do the partial derivatives. It's not the first time we are doing this one. When you are calculating the charge density using only the partial derivatives, then you get your 8 marks, simple like that. The electric field in a particular region, then you calculate the charge density in that region. This one is the easiest of them all. The easiest of them all. 8 marks giveaway. Just to do the
that
partial.
number 1, I'm not sure if I got it correctly, but I'll try to do it on my own. And then I'll ask you questions after that. I don't think I understood that one. Yeah, but let me try it on my own and see.
All right, we'll hear the questions.
Yeah.
Number C.
That one I got it. It's fine.
Partial derivatives. With respect to X, with respect to Y, with respect to Z. With respect to x, you get 2. With respect to y, you get what? 3. With respect to z, what do you get? 0, because 3 is just a constant. It does not have any function in terms of z. Then grad dot e is equals to 5. Any question? Number C. Then number 2, the 8 marks, just 2 minutes, you'll be done. Collect your 8 marks. Then let a cylinder has its radius 10 centimeters and the length is 1 over pi meters. So there it's like this, 1 over pi. Then the units in meters, that is the length. Determine the volume by integrating the cylindrical coordinates. Determine the surface area of the same cylinder when the top and bottom is closed. Top and bottom is closed for the cylinder. Oh, let's find the integrals. All right. Radius, we are told here, the radius is 10 centimeters. Convert 10 centimeters to what? To meters. That is, so 10 centimeters, it's 0.1 meters. Any problem here, everyone should know how to convert 10 centimeters to meters. You just divide by what? 100, isn't it? The length is 1 over pi meters. Volume via cylindrical coordinates, yes. So which means you are integrating dr. Volume element, it's r dr, d theta dz. That is the volume element. So whenever you are calculating the volume element, V is equals to that surface, dr, d theta, dz. So now it's a matter of you putting your length, it's ranging from what to what. Remember, this is a what? It's a cylinder. So
You
the
say?
cylinder.
Can I ask, how did we get those coordinates?
Which coordinates?
The one that is for ranging from 0 to L, 0 to 2 pi, and 0 to R. The integral.
This is your L, isn't it? Length of the what? Of the cylinder. Remember, this is the central point. And it's closed. They were told that it's closed on the both surface. It's closed here. And this side is also closed, which means it's a surface. So the L is this one. Length of the cylinder is ranging from 0 to L. It's ranging from 0 to L. And your theta, remember, if you are calculating the volume element, theta, remember, if you are positioning the cylinder facing upwards like this, if it's facing upwards like that, which means this, like this will be your Z plane. So along the Z axis, we have to draw it like this, along the Z axis. Let's use a different color. Along the Z axis like this. Your cylinder is passing through along the Z axis and down there. Then your theta, the theta that you are talking about, to say the theta is ranging from what to what. Remember, the theta is the one that is checking the rotation. This rotation, the theta, you are rotating for how many degrees are you rotating? Isn't it a circle? A circle, when you're rotating in a circular way, how many degrees if you rotate? 360. So it's a cylinder, theta, 360, which means for you to form a cylinder, you don't rotate only half. It's 360 degrees, that second. So you're talking of now in cylindrical coordinates, it's r, theta, and z. So these are, you must know, whenever they talk of cylindrical, they are talking of r, dr, d theta, and dz. So your theta is the rotation of this cylinder. If the cylinder was cut into half, which means the rotation or the volume of that one into half, it won't be from r to 2 pi. It will be from 0 to pi, because half of 2 pi is pi. If it was cut into half, the volume is no longer from 0 to 2 pi. It will be 0 to pi. But because it's full, it's 0 to 2 pi. I don't know if your question is answered. In terms of theta, it's rotating throughout. It's a circle. Then the z
ranging from 0 to 2 pi.
is ranging. This is z equals to 0. It's on the surface, on the x-axis. 0 to L. Where is it ending? At L, the length of the what? Of the cylinder. So Z is on the surface, 0. Z is 0 up to L. Then the radius of the cylinder, which means dr, d theta, dz. So the radius is ranging from what to what? If there is no circle, it's 0, which means we don't have any circle at the bottom. So 0 to r. So this is the radius r, which they are referring to. 0 to r, 0 to r, like that. Any question? For the base, 0 to r. So now you are integrating r, dr, d theta. So is the problem the mathematic part, or is the problem the setting up of the integral, so that we know what to talk about? If it's the math part, then you tell me. If it's the setting up, then I've shown you where the limits are coming from. These ones, which you were asking me, where are they getting them from? And this, always you add this, it's always adding r, you always add it, r, dr, d theta, dz. That is the volume element. Always add dr, d theta, dz. Any question? Do you know how to come to here, if I'm to ask? Hello.
Hey, say
Eh?
no.
So which means your calculus is very bad if it's like that. All right, let's integrate then. What is the integral of r? What do you get? If you integrate r, the integral of this r
Squared over 2.
was, if you can't integrate this one, guys, how are you surviving in maths? All right. Which is equals to the integral of 0 to L. Then you put integral of 0 to 2 pi, like that. So now I'm integrating what? R. If I integrate R, what do I get?
R squared over 2 plus C.
So it's R squared over what?
Over 2.
Then you put it in brackets like this. Put it in brackets like that. Then you substitute the limits. 0 to what? To R. Then you indicate d theta, d what? dz. We are done with r dr. So it means you are now replacing the values. So what I've put in the square bracket, it means where there's that small r, we are going to replace it with what?
The big R.
The big R. Then you subtract minus. So you'll be doing this. You'll be saying R, where there's the small r, I put the big R first. So it will be R squared over 2. Minus, where there's a small r, now we put small 0 squared over 2. That is what it means, this square bracket and the r and the 0. So at the end of the day, if you subtract, you are going to get what? R squared over what? Over 2. Any question?
Mm-mm.
All right, so let's replace it now. So which means from there, what are you going to write? You are going to say this is the same as, this is no longer physics now, it's maths now, what we are doing now. If you had told me that you understand, you would go on to the next question. 2 pi, which is r squared, capital letter r squared over 2. Then you say d theta, d what? dz. Then what are you going to do there? When you integrate with respect to theta, what do you get? R squared over 2 with respect to theta.
0.
Integral. You differentiated and you got r squared over 2. So what was the original? Just like what we were doing in calculus that day. Integral
It's R.
over L. Then now the integral of r squared over 2 with respect to what? This integral. With respect to theta. You are differentiating with respect to theta. The outer limit corresponds to dz. The inner limit corresponds to dr. So here the middle limit, this one, is corresponding to theta. So integrate this with respect to what? To theta. What do you get? What do you get? R squared over 2. Integral of r squared over 2 with respect to theta. What do you get, class? Maith, what do you get? It's theta. It's theta r squared. Theta r squared over 2. This is what you differentiated. D theta of theta r squared over 2. When you differentiate theta, you get 1. And what is 1 times r squared over 2? It's r squared over 2. Then you write dz. Any question?
The R that you're talking about is that small R.
It's the constant which is there. It's not the small r, the capital letter R. The small r we are done already. We are no longer talking of the small r. We are left with 2 integrals. Small r, we dealt with it already. That's how you move from triple integral, moving one by one. So now integrate theta r squared over 2 with respect to z. What do you get? If you have understood. We want to replace now the integral, whereby I must substitute the limits L and 0. And here I have to substitute the limits 2 pi and 0. So I put my limit 2 pi there, and then I put my limit what? 0 there. Then I evaluate. So which means where there is 0, I ignore the limit because any number times 0. Where there is theta, I put 0. So which means it vanishes. It becomes what now? From here, what am I going to write? So which means it's the integral of 0 to L of 2 pi. Where there is theta, I replace theta with 2 pi. That's what it means. With the 2 pi r squared. Where there is theta, I'm replacing with 2 pi. R squared over 2 was already there. I did not change. So now I integrate again with respect to dz so that I get the final answer. What is the answer here? The integral of 2 pi r squared over 2 with respect to dz, with respect to z. What do you get? Integrate. What do you get here? It's equals to what? Now the integral is out. You are just left with square brackets like this. What should I put inside?
So the thing that is confusing me is that R. I get it, the R.
The r left already. The small r left already. It left already here when we replaced it with the big R. We said the integral, what is the integral of this R, small r here? What is the integral of the small r? You told me it's r squared over 2. So by the time you put r squared over 2, this integral, it vanishes, that integral, because you've already integrated. To say, if I integrate that one, it's now r squared over 2. Then the limits, you put them there on the bracket. To say the small r, where small r is equals to big R, where that small r is equals to the big R, that small r is equals to the big R. And also where the 0 is also equals to that r, that small r. You replace into the integral so that we evaluate, we get rid of that square bracket. If I put this capital, that big R inside r squared, it becomes r squared over 2 minus 0, it's just r squared over 2. And then you continue with the integration, which means this bracket, square bracket, it goes. Then what are you left with? You are left with this bracket now, which is r squared over 2. You do the same. So I'm saying when you repeat again now, we are integrating now with respect to theta. R squared over 2, integrate it with respect to theta. We are just adding theta because when you differentiate theta r squared over 2, you are going to get r squared over 2 with respect to theta. Then once you are done, that bracket and the integral, it vanishes, which means this goes, everything, it goes. What are you left with? With the square bracket, where you have put r squared, theta r squared over 2, and the limits, they now come on the right-hand side of the square bracket, which is 2 pi and 0 dz. You integrate again. That's what I'm talking about. But before you integrate, you replace these limits first into the what? Into the square bracket, where the theta is 2 pi. So where there's theta there, you are replacing theta with 2 pi, which is this one. You put 2 pi, r squared over 2. Where there's theta, you replace with 0, you subtract. But we know any number minus 0 is 0. So there was no need of me writing again 0 r squared over 2, because I know it's just 0. So this is what is remaining. You integrate again this so that we are integrating with respect to z, so that I remove the integral. Then the answer there, it's z pi r squared over 2. That is with respect to what? To z. Then the limits comes there. Here there's L, here there's 0. Where there's z, that's where you are putting what? L. So which means your answer is L. Pi r squared over 2. The 0 is just subtracts. So that answer which is there, which is this one, which is there on top. Any question there? This answer which we have got here is this one, which is there. It's just the way, just subtracting it bit by bit. And the 2 pi, remember the 2 pi is still there. The 2 pi is still there. It's not pi, it's 2 pi. There. The 2 is there because we did not remove it. What we added was the z. So there, the 2 pi is also there. The 2 pi is also there. So don't forget. Let me put it. The 2 pi is there. It did not go away. The 2 pi is there. So it's 2 pi L 2 pi r squared over 2 is just half r squared. That is the integral. This you must know, class. It's not physics, this one. It's maths. Maivi,
Hello.
you don't know how to integrate a triple integral up to now?
No, that one was just a bit confusing because of the part that I didn't understand. It was that R where you were replacing, but now that you're doing it.
What was your question? Is it answered for that R? Or we still have a question where you didn't understand? Ask. Because we are explaining these solutions. When you're alone, you find out now you want to see what happened. Now you don't understand. That's when you end up memorizing, which is not good.
No, I agree. The big R, you replaced it where we integrated the small R, and then
Yes, you
then
replace. Yes, that's when it came in. Then the small R vanished. Yes.
and now when we do the second one again, it's this one where you said theta times R squared over 2, ne? So now, because the answer you found the two thing, what then happened to the R, this R squared over
The
2?
R remains. The R remains. We are not integrating. R is a constant when you're integrating with respect to theta. R will be a constant when you're integrating with respect to theta. It's a constant. It does not go. And when you replace those limits 2 pi and 0, you are replacing into theta, not into R. R is a constant. And once you have put 2 pi R squared, now you integrate with respect to Z, this Z, this one. After you have integrated with respect to this Z, then you add a Z because pi R squared over 2 is a constant. Like that. Any question? So we have found that when you simplify this, which means you are dividing 2 divided by 2, it cancels out. That's why you are left with pi multiplied by r squared times L. So the final answer there, if you simplify this one, we are saying 2 and 2 cancels. So we are left with L pi r squared, which is just here, they just rewrite. They started with pi r squared L, which is the same. So what is pi? What is the radius? What is the length? Everything were given. The length was 1 over pi meters. The radius was 10 centimeters, which is 0.1 meters. Pi is just a number, constant. So volume in cubic meters, because this is meter, a meter times a meter square will give you a cubic meter. M squared times m cubed. So this is the volume. Any question? So you replay the video if you didn't understand. So we still have surface area, which you need to explain again. I forwarded the questions. Go through them. Where you feel you did not understand, tomorrow we need to finish this question paper. So it's because you had not gone through it, you are seeing it for the first time. That's why sometimes it might delay, but go through it tomorrow. Yeah, we have to finish so that we do more question papers.
Okay.
So go through it. There are not many, only 5 problems.
So can you please remember to send us the one for calculus?
Yes, you just write again on WhatsApp the list of the things so that I sometimes forget. That's
I
fine.
wrote. Should I write now?
Yeah. Right. Okay.